Today I want to talk about software and graphs. And the reason why I want to talk about software and graphs is because I want to talk about managing software complexity by thinking about graphs. And what is a graph? A graph is something that has a series of nodes and edges, right? So I'm not talking about a bar chart or any of the other like business kind of graphs. I'm talking about graphs where we have nodes with these circles and they're connected up with edges, which are lines. And so if we're going to think about software in terms of nodes and edges, we need to know how to map software onto a graph. What is a node? What is an edge? So let's look at that. The nodes are functions and data, right? So it could be a variable, could be a constant, could be a function, right? Could be some sort of method on something, and it's the interplay between those, right? So the actual variable, the actual function itself is a node in our code, right? For the purpose of this talk. Edges are the relationships between any of these nodes. So there can actually be relationships between two variables, or between two functions, or a function and a variable, or any combination of the two. So we could visualize it a little bit like this. So in this case, we have a very, very simple graph where we have a variable and a function, and there's a relationship between them. Now, what's interesting about this relationship is that it could be either way, right? So, which is why I didn't put any arrows on the line, on the edge, because this could be a variable that is being fed in as an argument to this function, right? Or the variable could be set by the output of this function, right? So those are a couple possibilities of how a variable and a function could be related. So in this case, for this presentation, I'm just going to draw a line and not show any directionality of what's going on. So the other thing that we could do is that this is actually a recursive thought, right? Here is an example of a graph that's at a relatively low level, right, of the actual text of our program where we've got variables and functions. But we can zoom out on this. We can group together our variables and functions, our data and functions into modules, and we can connect those modules together in a graph, right? We could have tons of these things, right? I'm just showing three because I want the image to be understandable, but we can connect these together. We could zoom out even further and connect modules together into an application and have applications live in an environment, right? There could be many applications that all connect to each other in an ecosystem, right? An example of this would be the internet, where we have all sorts of applications connected to all kinds of computers all over the place. So this is the idea that I want to talk about, right? This is how for the purpose of this talk, that we are going to map our application onto the idea of a graph. So with this in mind, how do we take this idea of programs as graphs and use that knowledge to reduce complexity? Well, there's a couple things that we can do by looking at the graph. We can reduce the number of nodes in the graph, and we can also reduce the number of edges in the graph. Those are really the only two options that we have to reduce the complexity, because if we have, say, two nodes, that's going to be very simple, right? Because there's only going to be one connection between them. So in order to understand this, right, which are more important, the nodes or the edges? Where does the complexity come from? Well, we can take a look at it. We'll go through just a couple of examples. And here's a graph with two nodes. There's only one way to connect them together, right? And here's three nodes. There's three ways to connect them together. There's four nodes, and there's 6 ways to connect them together. Here's 5 nodes, and there's 10 ways to connect them together. So we can see a pattern here that every time we add a node, there seems to be way more a way higher number of possible edges that we can use to connect these nodes together. And in fact, we can do a little bit of math, and we find out that the number of possible edges in a graph is the number of nodes times the number of nodes minus 1 divided by 2. So we can start to calculate these things, and we can see that, oh, you know, for 2 nodes, there's only one possible edge that we can have. And these correspond to the pictures I just showed. So you can see that the number of edges is starting to grow a lot compared to the number of nodes. The number of nodes is growing linearly, but we have a nonlinear growth in the number of edges. Right? In fact, we can go even further and go by powers of 10, and we can see that the number of edges just gets huge compared to the number of nodes. Look, the number of nodes here is 4.5 times the number of edges is 4.5 times the number of nodes. But over here, we're up to nearly 500 times as many edges as nodes, right? And keep in mind that this is the maximum number possible of edges for a fully connected graph. So this can be, so we can see that the number of edges can grow an enormous amount compared to the growth of the nodes. And I like to call this semantic software spaghetti, right? Because these edges are the relationships between the functions and data in your code. And so these relationships don't have a visible presence in your application. You can literally see your variable because you literally type the variable in. You can see the function because you type the definition of the function in. You can see yourself calling the function. But what you don't see is the implicit relationship between all of these things to each other. There's no real physical thing. And so what we end up having in our programs is a semantic software spaghetti, this kind of unseen web of complication that occurs in our programs. And this terminology goes back to the software or spaghetti code, where in the days before structured programming, we used to use gotos and jumps for everything. So you would just randomly jump, well, not random, but if you wanted to reuse a piece of code, you would jump down to an area, you'd do the code, and then you'd jump back. And if you wanted to loop, that was all a bunch of gotos. If you wanted to branch, that was you used gotos. And what's interesting is before structured programming, there was no limit on where you could jump in a program. So you could jump into the middle of a loop, and then you could jump out of it. You could jump into the middle of a function and then jump out of it. And what this did is this created this complected program, basically unreadable programs. And this was called spaghetti code, right? Where the path of execution just could go anywhere, and it kind of intertwined with itself. And in order to solve that spaghetti code, we created structured programming, which had very defined groups of instructions, where we have an if statement where we group blocks of code together, and we say, if a statement is true, we execute this block, otherwise we execute this block. And for a function, we have a block of code where we enter the function and then we exit the function out another end. We don't have randomly going into a random spot in a function. There's always an entry point. There's always a known exit point. And so this allowed us to dramatically simplify our programs and allow us to build more sophisticated programs. And so what we are seeing here is semantic software spaghetti. So instead of a explicit moving around in the program and jumping around, what we see are implicit connections between variables and functions that create complexity. And so this is just another example, right? What if we had 10,000 nodes? That would be around 50 million edges. So think about a piece of software like Firefox or Chrome, right? Firefox has approximately 25 million lines of code currently. So they probably have at least 10,000 nodes. Probably at least, how many functions and variables do you think they have in Firefox? at least this much, right? They probably have 100,000. But that means that the maximum possible number of connections there is going to be in the millions, right? So anytime you want to do something, you want to change or update or find a bug or fix something in Firefox, it's going to be very difficult because there are so many connections there. And that's what we want to avoid. So where do these edges come from? Like, where physically in our program can we look and see that these edges occur, right? How do we add edges into a program? Well, the edges come from an API, right? The API is what defines the connections between things. And for the purpose of this talk, an API is a very general thing. It could be a network endpoint, and that allows different applications to talk to each other. It could be function calls to a library or a package or some other way that we package things up. It could be assigning a variable. Assigning a variable is where we connect one value to a variable, or the output of a function to a variable. It could also be just a function itself can be an API. And so let's take a little look at that. Here's a distance function that finds the distance between 2 points, right? x1, y1, and x2, y2. And this function has 4 inputs, or 4 input edges, and 1 output edge, right? So every place where distance is called in our program, where we use distance, we are adding 5 edges to our program, right? So this is one node with 5 edges, right? So you can see that it's very easy to add lots of edges to our programs, right? Even at the very low level. So how do we get all of this complexity under control? We have all of these invisible connections. And how do we figure out where these things are? How do we control them? Well, there's really only 2 different ways. One, we can start to remove nodes. And in fact, this is probably the most effective way to get complexity under control. So for every node that we remove from our program, which means variable or function or class, for everyone that we remove an enormous number of possibilities for connections, right? So by far, the best thing that you can do is to make sure that your program has the least amount of code possible, right? You want to remove anything that's not necessary to perform the computation that you're trying to perform. The second thing that we can do is to control the edges, right? To design the ways that we connect things up together, right? So the question is, it's pretty easy to understand how we would remove nodes, right? It may not be easy, but at least conceptually it's easy to think, oh, I can look through my program and see where the unnecessary parts are and remove it. But architecting the edges is a little bit different because it's an invisible thing. So let's take a look at program topology, because that's really what we're talking about when we focus on these edges. The edges are how we connect things up. And so when we start connecting things up, we start creating topologies of these things. And so the ideal program would be something that just goes from top to bottom, right? There's no branches, there's no looping, you just do one thing after the other. And that would be the ideal program because it would be very, very simple. Now the thing is even though that would be simple, it's probably not going to be very useful. Most useful programs have some sort of branching logic, looping logic, in order to do really useful things. And so this ideal program, most of the time, is not going to be useful to us, this topology of a linear program. But we can try to keep to this ideal as much as possible. So the next best thing, right, is to have chains of dependencies or chains of relationships, where this single line down the vertical point is kind of our main computational line, right? This main chain of computation where we have some sort of logic here and we call into some other logic somewhere else, right? Or have a dependency somewhere else. And every once in a while, we may have to take a detour, right? So maybe we're loading in some files here, and then we have to do a fast Fourier transform because it's an audio file. Well, we take this detour into these dependencies that allow us to do our fast Fourier transform and some other things. And then we come back from these dependencies and go along our single train of thought, right? Our train of computation. And if we try to stick to this kind of topology, our program will be relatively simple because the connection between any two the connections for any nodes are going to be relatively small, right? So if we have to replace something or update something or move something, there's not going to be that many connections, right? Which means it's going to be easier to understand. It'll be easier to update. And it even makes it possible to just rip out a node and replace it with some other implementation. Very useful. So what if we can't do that, though? What if the shape of our problem requires us to create a different program? And at this point, I do want to talk about that the shape or topology of our program should match the problem that you're solving. So if the problem that you're solving is linear, and the algorithm can be expressed in this linear transformation of programs, then your program can be linear, right? If your problem is recursive, then it should probably if your problem is recursive, your program should probably follow that topology, right? So that's what we're going to do. So the next more complicated topology is a tree, right? Now, it doesn't have to be a binary tree. It just means that a tree of some sort, right? And the idea is that there's kind of a flow of dependencies from kind of top to bottom. And there's going to be a bunch of leaf nodes that don't really have any dependencies whatsoever. They're standalone. You can rip them out and put something else in, and there's basically no effort to have to do that. And the idea is you want to have as many of those as possible. You want to have something that has no dependencies on it as much as possible. And then the other ones that do have dependencies, well, let's try to make those dependencies few, right? We're not going to have many of them at all, right? And that gives us this nice little tree thing. And this also allows our code base to be navigated pretty easily, right? Because we can follow the logic from one part of the code base to the other and be like, oh, I need to have this dependency, and this dependency has this dependency. Basically, traveling a path along here requires only log n number of movements, right? So that allows us to have a relatively large code base. Even if the tree is very deep and we have a huge code base, a person, an individual, can still navigate through the code base relatively easy, because this node over here doesn't have some kind of crazy relationship to some other node on some other way part of the program, right? Everything follows kind of this logical progression. Now, sometimes we need even more complex ways to link up our programs together. And so the next kind of worst thing is to have a star topology, right? So that's where we decide, okay, we do actually need a bunch of dependencies or a bunch of connections. So what we're going to do is we're going to concentrate those dependencies and connections into just a few nodes, right? And there will be a few popular nodes, and they're going to be surrounded by a bunch of nodes that have very little or no dependencies or connections whatsoever, right? So that way, it still allows us to have most of our code be very simple, right? If you look at this, most of the nodes here are very simple, and we've concentrated these things into just a couple nodes, right? And it turns out that this kind of topology occurs very often in nature, right? Especially for relationships among people, right? So we see social networks naturally form this kind of star-like topology, where there's a few people who are very popular, and then there's a bunch of people who are less popular, right? And it turns out this is very scalable for networks of relationships. And in fact, this is actually how the internet, the topology of the internet is. So it has a few very connected nodes, And then there's a bunch of nodes that have very little or maybe just one connection. In fact, the vast majority of them are client PCs, like your phone or your computer that's just connected to your Wi-Fi, and that's one connection that goes back out into the internet, right? And then there's a few ISPs that have tons of connections to them, right? And it turns out this is a very, very scalable thing. It creates a complexity that's manageable. So this star topology is pretty good. The next worst thing, now keep in mind that we're actually getting to more and complex as we go on here. So each one of these things is actually worse than the last. The best is actually towards the beginning. So the next most complex thing is a planar graph, right? So a planar graph is where you could visualize your program on a piece of paper, and you could have all the nodes be aligned, all the nodes be on the piece of paper, and you can draw all the edges, and none of the edges cross each other. So if you can do that, if you can draw a graph where none of the edges cross each other, you have a planar graph. And if you restrict yourself to this, then you can actually control the complexity. Like, there will never be a node that has too many connections, right? And the entire graph will have a certain maximal complexity to it, right? Now, the worst possible thing that you could do is to have just a general graph where any node could possibly connect to some other node, right? And this is what usually happens in software development. Everyone who has been on a large project and who has started from the beginning of the project will know this feeling, right? You start the project and you have a lot of progress. There's a lot of productivity. But as the project goes on, as this code base gets bigger, productivity goes down. You have to hire more software developers in to get the same amount of work done. And the reason for that is all of these invisible connections that happen in the program. And what happens is the program becomes very difficult to understand, right? And because it's difficult to understand, it's difficult to modify, it's difficult to update, it's difficult to change. If I want to rip out a node here, that causes tremendous problem to a bunch of other nodes. It destroys all of my tests that I have. So what happens in this kind of environment is people try not to change the code that's already there. So what they do is they build other code around it. And this becomes a big ball of mud where notice that if we keep adding nodes around this graph, right? First of all, it creates the possibility for many, many more connections every node that we add, but it also increases the surface area of this whole thing, right? So if it goes from a small radius to this bigger radius, right, there's going to be a whole bunch more nodes, right? And so you keep having to hire people to create more nodes, and those nodes all get connected in random ways and make the whole thing even more complex. So this is what we want to avoid. So how do we avoid this thing, right? So now that we have kind of an idea of topologies, how do we get away from this thing? Well, we need tools, right? We need tools to help us visualize these things, because all these connections, the only thing that we can truly see here when we look at our code is the nodes. So when we look at the nodes, there's really no difference between this and this when we look at the code. There's no difference here because all we see is just 9 different nodes. And we are just like, oh, well, this code has 9 nodes. This code has 9 nodes. Oh, and they're organized. Good, all right. I put my code into a module. I put it into a package, or I put it into a class. Therefore, it's modular. But that doesn't mean that it's actually modular, right? It could be connected to all kinds of different things and have this tremendous amount of semantic spaghetti. And so even though a program may have the same number of nodes, one program may be way less complicated than the other based on just the topology of these invisible connections. So what we need are tools that can make these invisible connections visible, right? So we already have tools that can do things like look at a call graph, right? So we can run a program and see the call graph that happens. Well, what we need now is tools where when you hit compile, it will bring up an image and you can see the semantic graph or the code graph, right? And it could even be colorized where it could show you, hey, these parts are doing great. You know, this part is way too complex. You should focus on that. And this part is, you know, kind of in the middle, right? So it could show you in the graph, and you could zoom in and zoom out just like we had at the beginning of this talk, where we could zoom in and zoom out and see different abstraction levels and connections at the abstraction levels. You could do that with these tools. And how cool would that be to be able to actually visualize these invisible connections? So once you could see that, you could start to look and unravel things, right? And especially when you're creating a new project, right? As you're creating the project, every time you hit compile, this would come up, and you could even run different analysis algorithms, graph analysis algorithms on it, and it would tell you things that you need to worry about. And so what you could do is see the parts of the program that are starting to become complex. And you could say, oh, I can refactor this, right? If I take this module and I break it up into 3 different ones and take these 2 and merge them into one, right? I could reduce the complexity by a factor of 10, right? And so you could start to reorganize your code as you're doing development, right? So that way the complexity never rises above a certain level, right? You could control, and you could say, I don't want my complexity to rise above a certain level. When on my continuous integration build, if the analysis says, oh, you go over this complexity level, it needs to raise a red flag and send emails or whatever. And that would allow people to maintain productive velocity over the course of a project. So instead of these invisible connections just becoming exploding and just destroying productivity, what you could do is, as you develop, you could maintain the software in such a way that you maintain productive capacity, right? Productive velocity. And that would give companies a tremendous advantage over other companies that did not do this. So if there's anyone who creates any of these tools, or knows of any of these kinds of tools, please let me know, because I'd be very interested in looking at them. And that's about all I have to say.